any of that there. So again, we want to balance our equation. We want to convert grams to moles, mole to mole relationship, and moles to some other unit. And again, that's going to allow you to properly sort of solve for what is being asked. The other important thing that we talked about in terms of stoichiometry is, and again, sometimes people think that you do need to kind of go across the arrow, but you definitely could go from reactants to products, uh, products to reactants. And as I mentioned before, you could stay on one side of the arrow and do either reactants to reactants or products to products. The calculation and really the steps are the same. So you could really relate anybody in that equation to something else. All you really need is kind of like one piece of information, and you can pretty much figure out how everybody else might be changing this reaction. Any questions on basic stoichiometry problems? Okay, then we're going to talk about a little non-basic stoichiometry problems, and that involves what is sometimes referred to as limiting reagents. Some people may call it limiting reactants. Same deal. And basically, the idea behind limiting reagents is no matter what you do in a normal sort of chemical reaction, there's always going to be one reactant that pretty much gets used up first. So there's going to be one reactant that will get used up first in that reaction. And then you'll also usually have a reactant that is, you got plenty of it, and you'll still have some of it left over when the reaction is done. So that reactant that gets used up first, or that reagent that gets used up first, is what is known as the limiting reagent. And that, again, as I mentioned, is the one that will pretty much get used up first. And the importance of that is, for example, if we just have this basic reaction of A plus B makes A and B, clearly to make our product, we need an A and a B. And let's just say, for example, A was our limiting reagent. Once we use up A, would there be any way to make any product? There would be no way to make product at that point because you need one of each. So the importance of a limiting reagent is it is always the one that determines how much product you can produce. So the limiting reagent is always the one that determines how much product you can produce. So that's why when we come across sort of a limiting reagent problem, we do have to take that additional sort of step in our calculation to first figure out which one is the limiting reagent. And once we do that, we can then figure out pretty much how much product we can make. Now, the other reagent that is there, or reactant that is there, is what is known as the excess reagent. And as I mentioned before, the excess reagent is the one that you have plenty of. And you have so much of it that, as I mentioned, at the end of the reaction, you'll still have some of it left over. So that's why it's known as the excess reagent. So when we have limiting reagent problems, we do need to figure out which one's the limiting reagent and which one's the excess reagent. And as we'll talk about, once you're able to determine one or the other, so if you know, for example, which one's the excess reagent, you can know by default the other guy would be the limiting reagent. Or if you figure out which one's the limiting reagent, you'll be able to know which one is the excess reagent. So that's one of the nice things about it is if you kind of figure out one, by default, the other one is the other guy there in terms of excess or limiting. Now, there's a couple of different ways, or really there's several different ways you could solve these type of problems. And we're going to talk about two different ways, and you could choose as to whichever way you want to do it. But the way we're going to really kind of talk about solving these problems is based off of the same way that we do basic stoichiometry problems. So the nice thing about it is you can kind of do the same thing, which means if you have a limiting reagent problem, you should still start with a balanced equation, no matter what method you use. The next thing you should do is convert what they give you into moles. And right about here in the method we're going to do here, we're going to do a calculation to figure out which reactant is the limiting reagent. Once we figure that out, we can then pretty much roll with our normal sort of stoichiometry problem. We will use the limiting reagent, and do the mole to mole relationship to our product. And then we will take the moles to some other unit if necessary. So one method to solve for it, and the one I'm going to basically talk about here is doing this. Now, a couple of things about limiting reagents. How do you know it is a limiting reagent problem? So the way you know it's a limiting reagent problem, because they very often will not in blinking lights tell you, hey, it's a limiting reagent type problem, is if you have enough information about both reactants, and really the information you have is enough to calculate the moles of each reactant, then it is a limiting reagent problem. So if you think about some of the examples we did last time, we pretty much just had one piece of information given to us, 1 grams about somebody, and that was about it. But whenever you're in a situation and you have a stoichiometry problem and you look at your reactants and the information given to you, and you have enough that you can literally get to moles, however you need to get to moles, but you have a way from the information given to you that you could get the moles of both reactants. I say both because in most cases it'll just be 2. And you have enough to get the moles of both reactants, then it is definitely a limiting reagent problem. If you don't have enough information to get the moles of each reactant, it is just a basic stoichiometry problem like we did last time. So again, that is really the distinction as to how you know it should be a limiting reagent problem or not. And again, in a lot of cases, they will not flash lights like, hey, this is definitely a limiting reagent type situation. Any questions on that there? So for example here, if we're going to react our workout people here, we obviously need 1 of each to make our workout buddies here. So 1 there, 1 there, 1 there, 1 there, 1 there, 1 there. At this point, we are out of workout people here on the right, which means that is our limiting reagent, as there is no way we could obviously make any more sort of workout buddies. This would obviously on this side here on the left, these guys would be our excess reagent. And another very common sort of question is sometimes asked in these type of problems is how much of that excess reagent is still left over. So for example, in this picture, we could easily just count. We have 2 basically of our excess reagent left over. So those are really, really common sort of questions that are asked in limiting reagent problem, which is how much product you're going to make, which is based on the limiting reactant, and how much of that excess reagent, for example, is still left over at the end of the reaction. By the way, when you do a limiting reagent problem, as we will talk about, in order to determine which one is the limiting reagent, you do actually need to do a calculation. So sometimes people think, oh, it's just like the smaller number of moles or whatever it may be, and that's not always the case. So there has to be some type of calculation that is done in order to determine which one is the limiting reagent. It may not always be kind of the smaller numbers. So it's really important that you do a calculation and not just go by the smallest number. So for example, here, if we look at this equation here, and we're going to start with 4 moles of our sulfur, and we're going to start with 20 moles of our SF2. And we want to know, how many moles of our product here we're going to make. So first off, I know this is a limiting reagent type situation because they already gave it to me, but I definitely have the moles of each reactant. So as soon as I see the moles of each reactant, or once again, you could calculate the moles of each reactant, that is how you know this is a limiting reagent type situation that's occurring. So we'll follow our basic steps here, which is we want an equation, which we have already. The next thing we want to do is convert to moles, which they already did for us, which was kind of nice. Obviously, if not, you would use the molar mass from the periodic table and do a little conversion. Now, because it is a limiting reagent problem, we balanced our equation. We got into moles. This is where we're going to do a calculation to determine which one is the limiting reagent. So one method to determine which one's the limiting reagent is to do just a very basic stoichiometry calculation between the two reactants. And the purpose of this calculation is to figure out one very simple thing. If you wanted to use up one of the reactants, you want to figure out how much of the other reactant you would need to put in there to do that. So that's kind of the basis of what we're going to be doing here. So in this case, we could choose either reactant. So in this first instance, I'm going to choose the sulfur. And I want to know how much fluorine is needed to use up all the sulfur. So that is basically the calculation I'm going to do here. And this is what's going to allow me to figure out which one's the limiting reagent. So I'm going to start with my moles of sulfur, which is 4 moles. I'm going to find the mole-to-mole relationship from the equation between sulfur and fluorine. And I can see for every 1 mole of sulfur, I have 3 moles of fluorine. So just a nice, small, little basic stoichiometry calculation here. 1 mole of sulfur, 3 moles of fluorine. Moles of sulfur cancel. 12 moles of fluorine is needed. So again, this little calculation here is simply to figure out which one is the limiting reagent. Now that I know how many moles of fluorine that I need, I'm going to compare it to how many moles of fluorine I started with. So I need 12 and I started with 20. Do I have enough in this case? I do have enough. So because I have enough, what that means is we just figured out that the fluorine is our excess reagent, and by default, our sulfur in this case would be the limiting reagent. Any questions on that there? Now, you do not necessarily need to do this next calculation, but just to show you that you could choose either reactant. It doesn't matter which one you choose, and it will tell you the same thing in terms of which one's the limiting reagent and which one's the excess reagent. So for example, if I chose the other reactant, and in this case, I want to know how much sulfur is needed to use up all the fluorine. So I'm going to take the fluorine that I started with, which was 20. Going to use the same mole-to-mole relationship, 1 mole sulfur, 3 moles of fluorine. And that's going to give me here 20 divided by 3, about 6.67 moles of sulfur would be needed. In this case, I would take the moles of sulfur needed and the moles of sulfur I'm starting with. Do I have enough sulfur in this case? I do not. So it tells me the exact same thing. It tells me that sulfur is the limiting reagent, and by default, the F2 would be the excess. Now, you don't have to do both. You could do one or the other. It doesn't really necessarily matter, in a sense, which one you use to determine which one's the limiting reagent. Any questions on that calculation? Now that we've done it and we've identified which one is the limiting reagent, it pretty much just becomes a regular stoichiometry problem at this point. We're going to pick up with step number 3 and use our limiting reagent. So the important thing, though, is when we pick up with step number 3, we want to use the starting amount of our limiting reagent, which in this case was the 4 moles of sulfur. So we're going to use the 4 moles of sulfur. We will now have the relationship between sulfur and our product, which is 1 mole of sulfur gives us 1 mole of the SF6. So 1 mole SF6, 1 mole sulfur gives us 4 moles of SF6. This technically would be our theoretical yield in moles. We could also, if we wanted grams, use the molar mass for SF6. I won't calculate right now. And we can also figure out, obviously, how many grams it would be, which would be like the 4th step that we talked about in a basic stoichiometry problem. Any questions on that there? So this is one method to solve limiting reagent problems. You do a little calculation to figure out between the two reactants, if you want to use up completely one of them, how much of the other one would you need? Any questions on that? Now, the benefit of doing that little calculation to figure out which one's the limiting reagent is this. In a lot of cases, if I wanted to know how much of my excess reagents left over at this point, I already have that calculation done for me. I don't have to go back and recalculate it because I already figured out that my excess reagent, I would need 12 moles of it. I started with 20. So my excess reagent left over would be our 20 moles, which is what we started with. I already did my calculation here. I need to use 12 moles of it. And that'll give me something like 8 moles of my F2 will be left over. And obviously, you could figure out how many grams that would be as well if you were looking to figure out how many grams. So by doing this little calculation here, if you're asked that question of, how much of the excess is left over, you actually have the numbers right there and you could actually do the calculation. Clearly, if you chose this one and you were asked that question, you would have to still go back and obviously do the top calculation to sort of figure it out. But you oftentimes will get lucky a lot of times and have that question there. Any questions on any of those steps there? All right, so what is the sort of alternative method that's really popular these days? The alternative method that's really popular to solve limiting reagent problems is essentially, I think we had to start with here, 4 moles and 20 moles, right? So the alternative method to do it is just simply do 2 calculations, basically. So you do one calculation starting with your sulfur. So you would take the 4 moles of sulfur, you would do the mole to mole relationship between sulfur and your product. And then you could use the molar mass here of your product to get to the grams of SF6. You then would do a second calculation starting with the other reactant. Do the mole to mole relationship between the other reactant and the product, which would be 3 moles of F2, 1 mole of SF6. Also, you can use the molar mass and get the grams of SF6. So the other super popular these days method of doing these problems is just to do 2 separate calculations. And what you're looking for at the end is whichever one produces the smallest number of product, either grams or moles really, will be both your limiting reagent and your theoretical yield. So that's the other popular one, and you would just get rid of the other calculation and really not use it for much other than just sort of a wasted calculation in a sense. So that's the other method of it. Nothing wrong with doing it this way. It's taught this way a lot. It's taught in books a lot this way, and it does definitely work. One of the downfalls of it is, in a sense, you still then have to kind of go back, and if you had like the excess reagent, how much is left over, you got to do another calculation and sort of figure it out. While if you kind of do the other method, you might get lucky in a lot of cases to already have the calculation done, and all you have to do is some subtraction. But there is really no downside to either one. And I don't care whichever one you want to choose to use, whichever one you like. But remember that the answer is not both of them. You got to throw out the larger one, keep the smaller one as your answer. Any questions on that? All right. All right. Why don't we try one here? Why don't you give it a go? Which of the two are the limiting reagent, and what is the mass in grams of FES produced? So iron is 5585 and sulfur is 3207. So take a few moments, follow the steps here. I'm assuming it's a limiting reagent problem because it asks you which one it is. Yeah, so follow those steps. Can see how we should approach this. So clearly here we are looking for him as product, and they were nice enough to tell us what his limiting reagent is, what we're looking for. But once again, if they did not tell us this is a limiting reagent problem, this two pieces of information right here is what really tells us that it is a limiting reagent problem. We have the grams of both reactants, which means we could definitely get to moles of both of those guys. So right there is really what you should look for in terms of knowing that it is a limiting reagent problem. So we basically gonna follow our same steps here with our insertion of our limiting reagent calculation. We're going to balance the equation, which it looks like it's balanced. We are going to then convert to moles here. So we're going to convert each of our reactants into moles. So we'll take our 6.83 grams of iron using the molar mass from the periodic table here, grams on the bottom so that they cancel. And that's going to get us there 0.122, it looks like. We'll do the same calculation for our sulfur, which is our other reactant. Using our molar mass of sulfur from the periodic table gets us 0.291 moles of sulfur. So once again, you can think of these as your starting amounts of each of these reactants. That means that we're now going to move on to our limiting reagent calculation. Once again, here, all you got to do is just pick one of the reactants and figure out how much of the other one you need to use it up. So here I will go with how much sulfur is needed to use up all the iron. So starting with my moles of iron, 1.122 moles. The relationship between iron and sulfur is a 1-to-1 relationship. So 1 mole of iron gives us 1 mole of sulfur. That means that I would need 0.122 moles of sulfur is needed. Again, once I figure out how much, in this case, of sulfur I need, I want to compare it to how much I am starting with. And do I have enough in this case? I do have enough. I need 0.122. I got about 0.29. So I do have enough. That means that that calculation tells me the sulfur here is our excess reagent and the iron is our limiting reagent. Any questions on that calculation? Once again, the importance of having to do this calculation is it is, again, always the limiting that determines how much product you make. So you got to determine that. Once again, you have to determine it from a calculation, not whichever one's the smaller number of moles. So you got to do the calculation to do that. Once we've done that, we want to make sure that we do go back and start with our limiting reagent amount. So basically, this was step number 2. This is our limiting reagent step. Now we're off to step number 3, starting with our limiting reagent, which is our iron. We now could go from our limiting reagent to our product. And from the equation, 1 mole of iron gives us 1 mole of our product here. So we'll do our mole to mole relationship. 1 mole of iron gives us 1 mole of our product. Gives us 0.122 moles of iron 2 sulfide. In this case, we are interested in how many grams. So we have to do step number 4 here, which is now I need the molar mass of my product, which is actually just adding these two together. So we'll just add those together. 5585 plus 3207 gets us 8792. Is our molar mass of FeS. So using that as our conversion factor here, the grams are going to go up on top. 8792 grams per mole from the periodic table Moles will cancel, and that's going to get us here about 10.7 grams of FES. This once again would be our theoretical yield in this case. Once again, a yield does has to be a product, so that is what that is. Any questions on any of those steps? Much like basic stoichiometry problems, you could combo these two steps if you wanted to and not get an answer in between and just, go straight through with the calculation. Now, again, the benefit here is, although it didn't ask for us in this particular problem, if we did want to know how much of our excess reagent is left over, which in this case is our sulfur, we know that we needed 0.122 moles of sulfur. We know how much we started with. So at this point, we could just simply subtract those two numbers, which is what we started with, minus how much we needed, which was there. And that gets us 0.291 minus 0.122, 0.169 moles of sulfur would be left over. And we can use the molar mass of sulfur there, 3207 grams per mole. And we'll end up with like 5.42 grams would be left over. So we started with about 9.34 grams. We used about 5.4. So just under 4 grams was used in this reaction of sulfur. And we still had about 5 and change of grams of it left over. Any questions on any part of that calculation there? Okay, let's try some more here just to make sure. Hopefully it comes up with the same numbers we just got. Looks like it. All right, let's try this one here. All right, so starting with this equation, if you started with 622.7 grams of NH3, the molar mass of NH3 is 1703 grams per mole from the periodic table, and you let it react with 1241 grams of CO2, molar mass 4401. How many grams of your product would you make there? And how much of the excess reagent will be left over? So take some time there and see what you come up with. Type of question where it really didn't ask you about the excess reagent or which one is the limiting. The way you again should be able to recognize it is we do have the grams of both reactants, which means that is definitely easy to get to the moles of both of those. So that is again the key piece of information that allows you to know that it is a limiting reagent problem. So whenever you have the ability to get again to moles of each reactant, you have to do the limiting reagent type part of the calculation. So first things first, we want to balance it, which is already done. We then want to convert into moles. So we'll take our 622.7 grams of NH3. Once again, if they did not give you the molar mass of NH3, you would have to go to the periodic table and look it up. And in this case here, it looks like 622.7 divided by 1703, little 3656. We'll do the same type of calculation there for our other reactant. Using the molar mass that was given to us of CO2. That's going to get us here 1241 divided by 4401. It's like 2820, we'll call it. Once again, this is really like your starting amount, right, of each of these guys here, those numbers that we got. So because it is a limiting reagent problem, we do need to now take a little sidestep here in the calculation and just do a basic little calculation to figure which one is the limiting reagent. So our limiting reagent calculation here, I'm going to see how much CO2 is needed to use up all of the NH3. So again, I'm just going to do that little calculation there. So I'm going to start with my NH3, which is 3656 moles of NH3. Going to the equation, it is a 2-to-1 relationship. So for every 2 moles of NH3, I have 1 mole of CO2. So we're going to use that as our conversion factor here. 2 moles of NH3, 1 mole here of CO2. So we'll take our 3656 basically and divide it by 2. 1828 moles of CO2 is needed. So once again, at this point, we're going to compare it to our starting amount here of CO2. And we could hopefully clearly see that I have 28 I started with. I only need 18. I have enough in this case. And that would mean once again here, this guy is going to be our excess reagent. And this guy here will be our limiting. Any question on that determination? Now, mind you, the couple that we just did, we did have enough. It won't always have enough. So if you did the other one, you would see you did not have enough, right? And it will tell you that the NH3 is still the limiting reagent. By the way, also a good reminder in this particular problem, the one with the larger number of moles actually is the limiting reagent. Yeah. So again, you have to determine it from a calculation, not just based on which one has a smaller number of moles. So you got to do that calculation to determine it. Now that we do have which one's the limiting reagent, we could just get back on our stoichiometry train here, and we'll start with the starting amount of our limiting reagent. And now we could go from our limiting reagent to our product and have that relationship. And as we could see, for 2 moles of NH3, we get 1 mole of our product here. And that's what we're going to use here to do our conversion. So 2 moles of NH3, 1 mole of our product. Those are going to cancel, going to get us 18.28 moles of our product here. And lastly, here we can use the molar mass that was given to us. And again, if it was not given to you to the periodic table, you would need to go to convert those into grams. So if we do that, and this would be kind of like our 4th step there, times it by 6006, looks like 1098 here. And once again, this would be our theoretical yield in this case. Any questions on any part of those steps there? Now, in this particular problem, it did want us to figure out how much of that excess reagent. And again, the benefit of doing it this way is we already have done that calculation. One for the second part of the question. So we know from our calculation here to figure out our limiting reagent that the excess that is left over, we started with 28.2 moles of CO2. That's what we started with. From our calculation, we see we need 18.28 moles of CO2. And that will get us 28.2 minus 18.28, 9.92 moles of CO2, which if we want a gram type number, we could use the molar mass that was also given to us here. And that would tell us here approximately, we'll call it 436.6 grams of CO2 would be left over. So in this particular reaction, we started with like 1,200 grams or so of CO2, and we still have about 436 grams of it left over at the end of the reaction. We use like 800 grams ish of it. Yeah. Any question on any of those steps? So again, if you did the other method where you just did two separate calculations, you should have hit the 1098 number, which should be the smaller of the two. You would just need to go back really and do the limiting reagent calculation so you can answer the last part of the question. So again, those are the steps. Any questions? All right. It's good. They got the same number, so that ain't bad. All right. Still got the same number, even better. All right. So let's talk about yields of reactions. So we've been talking a little bit about yields, and there's really three types of yields that we come across when we do stoichiometry problems. The first one really is what we kind of been calculating in a lot of these sort of problems, which is whenever you calculate a product, and by the way, once again, a yield should be a product. Yeah. So a yield does need to be a product. The theoretical yield is the maximum amount of yield that you should get in a reaction. It is based off of the equation and how much you're starting with, really, of the limiting reagent. And if everything went perfect, no side reactions, you didn't drop anything, nothing got stuck in a beaker, that is the maximum amount of product that you should actually produce in a reaction. The truth is, nothing goes perfect, as you'll learn this week, probably when you do the experiment on Wednesday. Stuff gets stuck in the test tube. We can't get it all out. Things are on your stirring rod. You can't get it off. And that brings us to the other yield, which is the actual yield. And much like the name implies, it is actually the amount of product that you made when you did the reaction sort of physically. Now, typically speaking, your actual yield should be smaller than your theoretical yield. It is possible that your actual yield will be larger than your theoretical yield, but that usually means you screwed up pretty much, and you shouldn't usually get that. But it does commonly happen sometimes. For example, like the experiment you're doing on Wednesday, you're going to make a precipitate. You're going to throw it through a funnel with some filter paper. You're going to take that filter paper off. And obviously, because there's liquid as well as when you're filtering it, that filter paper is going to be wet. So if you don't let it completely dry and you weigh it, you'll get a lot of water weight that's really not your product, but you're counting it as your product, and you'll end up with a greater sort of actual yield than your theoretical yield. So that's a very common error that people make, is they don't let the, say, precipitate, for example, on the filter paper completely dry out, and they end up weighing it too quickly. You get all that water weight, and you end up with a higher actual yield than you should. So it is possible in real life to do it, but it usually means you kind of screwed up somewhere along the way, and it's not usually a good thing. Taking both of these yields together brings us to our percent yield, which is very commonly what we look to try to do when we're doing stoichiometry type of experiments. Our percent yield is our actual divided by our theoretical times 100%. Usually when we calculate percent yield, we're looking for a big number. That means you did pretty well. Not a really big number over 100, because that means, again, as we just talked about, you did something not so well because you got over 100 yield. But if you have a small percent yield, you definitely lost something along the way. The good news in sort of book problems is the actual yield is usually given to you. So somewhere along the way, they'll just tell you, you produce this much of the product. The theoretical yield, you usually need to calculate from the equation, and it could be just a basic stoichiometry problem, or it could be a limiting reagent type problem. But one of those type of ways, you'll need to sort of calculate the theoretical yield, and then you just divide the two and times it by 100 in that particular case. All right, so let's try one here. Why not? Big numbers. There we go. All right, so starting with this here, 2.46 times 10 to the 4 kilograms of TiCl4, molar mass 189.7, reacts with 1.44 times 10 to the 4 kilograms of magnesium, molar mass 2431. What is the theoretical yield of Ti? And what is the percent yield if you produce 5.42 times 10 to the 3 kilograms here? I think the only other number you need is 4788 is titanium. All right, take a few moments there. In this case, we really want a couple things, the theoretical yield and also our percent yield, which is our actual divided by our theoretical times 100%. In this case, as I mentioned before, the actual is typically given to us. So we do have the top part there. The bottom part is going to come from a calculation. So we are given the starting amounts here really of both reactants. So once again, although they are not in grams, that should be the key to you, that you can get to grams and you can get to moles of each of these. So once again, that is the piece of information that tells you this is a limiting reagent type problem, and you're going to have to do that calculation. So we're going to start with our balanced equation, which it is. We're going to convert into moles. Here we have to do an additional conversion to take it from kilograms to grams, and then grams to moles using the molar mass. So taking our moles of TiCl4, we'll go 2.46 times 10 to the 4 kilograms. In 1 kilogram, there are 1,000 grams. That's going to get rid of our kilograms. Now we can use the molar mass from the periodic table, or actually, I think it was just given to us in this problem. So 180, use it correctly, 189.7 grams per mole here of TiCl4. And that is going to get us here as the grams will cancel. Make sure you use your exponent button times 1,000 and then divided by 189.7. Looks like we'll call it 1.30 to the fifth. We're going to do similar calculation here for our other reactant. So our moles of magnesium will be 1.44 times 10 to the 4 kilograms. Once again, I'm going to convert it into grams first. And now I can use my molar mass like I did above there for magnesium, 2431 grams per mole. The grams will cancel, and we'll end up with 592 to the fifth. 5.92 times 10 to the fifth moles of magnesium. This once again are really our starting amount of each of our reactants. So now that we have it in moles, which is really our sort of second step, we can now do our limiting reagent calculation here. So in this case, I'm going to figure out how much magnesium is needed to use up all the TiCl4. So that again is the calculation. We'll take our starting amount of our TiCl4. We'll go to the equation and find the relationship between those two. I'll circle the right ones there. And we can see that for every 1 mole of TiCl4, we get 2 moles of magnesium, the mole-to-mole relationship from the equation. So we'll use that. 1 mole of TiCl4, 2 moles of magnesium. Moles will cancel. And 1.3 to the fifth times 2, 2.60 times 10 to the fifth moles of magnesium is needed. So once again, we're going to take our moles of magnesium needed and compare it to how many moles we're starting with. And in this case, looks like we hit it on all 3 of them what we did. We do have enough in this case, yeah? So once again, we do have enough, and that's not always the case. You may, again, end up with not enough, which means it's the limiting reagent. So that would mean this is the excess. This guy here should be our limiting reagent. And remember, we do want to start with the moles of our limiting reagent to basically continue on here. So starting with our 1.3 times 10 to the fifth moles of TiCl4, we now could go from our limiting reagent to our product, which from the equation is a 1 mole TiCl4 gives me 1 mole of Ti. So that will be what we'll do next. I think I could do that without the calculator. 1.3 times 10 to the fifth moles of Ti. But since our actual yields in kilograms, we do want to convert these moles to grams and then to kilograms, so everybody's in the same unit. So I'm going to do those two conversions next, which would be like the fourth step. Using the molar mass of Ti from the periodic table, which is 4788 grams per mole. And then 1,000 grams in a kilogram, just to get everybody into the correct units, will give us 6.22 times 10 to the 3 kilograms of Ti. This would be our theoretical yield in kilograms. If we wanted it in grams, we wouldn't do the last part of the calculation. And if we wanted it in moles, it would be the 1.3 times 10 to the 5. Any question on that there? That now leaves the bottom part of what we need for our percent yield. So once again here, our percent yield will be our actual divided by our theoretical times 100%. Actual given to us at 5.42 times 10 to the 3 kilograms. Theoretical, we just calculated 6.22 times 10 to the 3 kilograms times it by 100%. And it looks like here 87.1% yield. Not terrible. Not too bad in this case. Any questions on that calculation there? Once again, like a normal stoichiometry calculation, if you wanted to sort of bridge these calculations together, you could without getting a number in between and just take it all the way to the end. Now, one last thing here about percent yield. The units doesn't matter as long as they're the same. So here we did kilograms divided by kilograms. You could do grams divided by grams. You could do moles divided by moles. As long as the top actual and the theoretical are in the same units, you could calculate the percent yield, but they has to be in the same units. Any questions on that there? All right, we'll lay it up there for today.